is dealing with finding obstacles. Is that okay? Yeah. Okay, Kim, floor is yours.
Thank you, Mr. Chairman. Yes, I was from Aarhus University, but I recently switched, so I'm in industry now. But we are collaborating, so it's good. We are Aarhus. Sales slide. Yes, so Peter was here talking about very sophisticated models for detecting obstacles in images. But he also told that the semantic segmentation models, they're very computationally expensive. So another way of looking at obstacle detection is a very simple approach. And the approach is that whatever we can see in the field that's not the field, that should be of a concern. So that's the part where we're doing the novelty detection. The other thing is that this approach is very simple. It doesn't rely on a lot of training data. It just looks at what the field looks like today and tries to calculate what's novel in the field. So what I'm presenting here is how we can apply that very simple principle and how well it will work for our application of row crop operations in the SAFE project. So just short the motivation. I think Peter was also presented that very well. And I'll present some of the idea, the core concepts of the novelty detection. That we're building a background model, and we're trying to apply field mask, saying we're only interested in detecting what's in the field and how we detect the obstacles. Then I'll show some results regarding how well it performs in detecting the obstacles that we have in the field, but also what this kind of idea could be used for future work, and then discuss and conclude that work. Yeah, so the motivation, we've seen the poster from the SAFE project, safefarming.dk, and we would like to have machines that are safer, not just robots that can drive autonomously, but also existing machines with very high working widths, where the farmer are driving at high speeds, or the farmer has problems. He's focused on the crops, and maybe he's not seeing what's 6 or 12 meters on the side of his machine. So trying to develop safer machines, but also working towards fully autonomous machines. And examples of obstacles in the row crop could be large rocks, erosion channels, trees, or other things. And they can reduce the quality of the work, but also cause damage to the equipment, or if it was a person, you could injure or kill that person in front of you. But as a supplier to the agricultural industry, we would also like to protect our equipment. And this is what happens when we're doing mowing, and we're not seeing this, this fairly large obstacle, but it's very low, and the machine we did some heavy damage to the machine by not avoiding that. So the novelty detection, it's a pretty simple model. We look at the field. We have a standard color camera. Look at how the field appears, and that's modeled by in the LAB color space using clustering. And the novel detection is based on the distance for each single pixel in the image to that model. So in that way, we can at every frame, for every pixel, we can calculate the distance to our background model. The background estimation is not based on changes in individual pixels. In background subtraction for surveillance cameras, you have very good models of how individual pixels, how they change in color or intensity over time. But since we're operating with a machine that's moving, we can't really focus on pixel level. We need to focus on image level and image appearance level. But we can still treat individual pixels and calculate the distance of that individual pixel to that background model. So the distance to the background model is what gives us what's novel. And the reason we can do that is that we see the field as one homogeneous appearance, one homogeneous field. So it doesn't really change that much apart from what's not supposed to be there. We also apply field estimation, and that's more like the inverse of background estimation. So we want to only apply our image processing on the part of the image where we have the field. We saw in Peter's images that we could have a road, shelter belts, skies. We'll try to use that same background model and just inverse it, and to obtain a small part of the region which we are focusing on. Of course, if we have obstacles within that field, these regions will be removed in that process, and we close that by using morphological closing. Furthermore, the field can change appearance over time. We're working in an outdoor environment, so we can have clouds coming in, covering the sun, and the light will change. We have trees that will have cast shadows on a local part of the field. So therefore, we update this background appearance every 2 seconds. And that update is based on a fixed part of the bottom of the image, which we know there are no obstacles there because we have not detected them beforehand. Also, when you change the background model, we also want to change how you detect the obstacles based on the threshold you apply. And that threshold is also updated based on the measured mean, distance, and standard deviation. So the way we detect the obstacles is to perform simple thresholding on the distance map, and then do a blob detection to filter out very small blobs, which could be noisy pixels, and also very large blobs, which could be false detection of maybe a shelter belt or a road on the side, which is not part of the field. So just to show you what we mean as a novel detection and the results that we obtain by this, we have the video here. We have an obstacle here clearly marked. All these blue bounding boxes are manually labeled obstacles, and all the red smaller boxes are what the algorithm says that's a novelty, that's something that's not supposed to be there. And as you can see on this first frame of the video, we have some of them where we are, that makes sense, we have obstacles here, but also some like this or this, it doesn't really make sense that this is an obstacle. But again, it's a very simple model. This down here is the track from the tractor, but it could also be an erosion channel. Further analysis will have to figure that out. Right. So if you just play the video here, we see we have fairly good detection of the person in front of us, and this is what the threshold of distance map looks like. You can see in the background we have a lot of large obstacles. This is the field estimation, so we're not sorting out a lot. We have very much large images the field. What's interesting here is that we're actually able to detect these very, very small obstacles. This is a hair, or teddy bear hair. It's not moving. But as you can also see, that we're experiencing some false detections down here, but most of our detections are actually placed on the obstacles or here, which is not part of the field. It's still a novel detection, right? But it's not labeled. Yeah. So this can go on and on. So what are the detection capabilities? Well, in the data we have analyzed, we have 60 obstacles. It's the hair, the small hair, it's persons, it's the green barrels that you saw in the video, and we're able to, at some point, driving towards them, we're able to detect 58 out of 60 obstacles in those frames. We detect, out of all annotations in the image, we detect about 32%, 33% of the instances, meaning that in some frames we're not able to detect the obstacle, but while we're driving towards it, in some of the frames we are detecting the obstacle. We have a lot of false positives, and that's mainly due to the fact that we are detecting the shelter belts and the grass beside the field as a false detection. And that's true in the sense that it's not an obstacle that we have marked that's in the field, but it's not a false detection regarding, it's still a novel part which is not supposed to be in the field, which it isn't. We also have some false negatives, and that's the detections where we are supposed to detect that there's an obstacle, but it's not, we're not detecting it. And that affects, of course, the number of true positives that we are able to detect. Some of the false negatives are also due to the fact that we have labeled all the obstacles at very far distance because we knew that they were there. And the algorithm is not, it is able to detect those obstacles very far away, but then we have to set the threshold in a way that a lot of noise and detection will affect our results. And I'll come back to that why we didn't choose that. Because, okay, so we're detecting, we don't achieve a lot of good result detecting the obstacles. We have a 33% true positive rate on doing that. But if we analyze how many detections we're actually doing per image, we're having an average of 11.45 or 12 proposed regions in the image per image. And that's measured over a total of 16,000 images, which are annotated. So we can actually do that. Yeah, I'll come back to that. Yeah, as I said before, so this simplified detection algorithm is not able to solve the problem by itself. But as you saw, that it proposes some regions that we can apply for further processing. And in that way, this very simple approach of a novelty-based detection can be used to provide proposals for more complex and time-consuming algorithms. An example could be the convolutional neural networks that we see outperform human detection capabilities. And furthermore, these models are actually being able to run on embedded hardware. This is the Jetson CX1 from NVIDIA, and it can run 258 images per second. Meaning that if we propose 12 images, or 12 regions per image, we can achieve about 20 frames per second. Some of the detections that then the algorithm will have to evaluate, is this an obstacle or not? And sometimes it will be that these more complex models will find that this is not an obstacle, this is just a field. But in 33% of the cases, it will agree that, it will agree that this was an obstacle. So this could improve the performance of the obstacle detection, and it can run on embedded hardware. So the conclusion is that this simple appearance-based background model, it utilizes the homogeneous appearance of the field, and in that way it can be used to propose regions for more computational heavy algorithms, and then you can actually apply these models to existing embedded hardware at frame rates that are acceptable for the speeds that we're running in the field. The future work could include tracking of the proposals. So if we have proposals that are very confident, frame by frame, we could say with more confidence that this could be an obstacle. And we could also use feedback from the recognition step in that sense. So if the more sophisticated algorithm has discarded a region in the image, we can discard that in the region process step as well. So, thank you.
Thank you.
Thank you very much, King, for this interesting presentation. Are there any questions? Yes, please.
10 minutes from the vertical hardware. Do you expect the same results when the crops are more grown or higher?
Actually, we see in the video that some of the crops, the small crops, are detected as an anomaly. And that's because when we are building the background model, we don't have a lot of crop material in the image. But when we have bigger crops, then the crops will also be part of the background model because they're part of the appearance of the field. And we have seen that in the grass mowing operations, where it actually performs better because the crop is covering most of the field and the homogeneous appearance is clear. So I won't expect that to be a problem. One problem, of course, is that you need to be able to see the obstacle. So if the obstacle is hidden in the crops, that's not easy. But that's the sensor. So.
That's a question. You mentioned that you tested in grass land, and what about detect deer kids or deer fallen? Is this possible?
It is possible if we're able to visually see the deer. The problem with the deer is that they're hiding in the grass, right? So if we want to be able to detect a deer with this, and we're mounting the camera in front of the tractor, at the time we are seeing the deer, it's too late. So other sensors or other camera placements should be applied in that sense for the deer. But for the big trees, people that are visually there, this can be applied.
Okay, if there is no other question, I thank you again. Thank the presenter.